This is 2015 Level 2 Waves exam. For this video I'll be working through question 4. Right, question 4. Tom and Alan watch waves in the ocean. The diagram below shows a wave crest approaching a gap in the seawall. On the diagram, draw the wave crest after they've gone through the gap. This is different. So I'm going to put up here diffraction. Diffraction. If you don't know what it is, look it up. We have waves coming in, so let's just note the wavelength before we start drawing stuff. So let's call that lambda. So because this here, the wavelength is pretty similar to the gap size, we're going to get diffraction. In fact, if we measured it up, this might even be greater than that slit, which should imply that you shouldn't get very much diffraction at all. But I'm guessing they're trying to aim for it being very, very similar size. So we should get a nice diffraction pattern like so. I'll just move some stuff out of the way. And this is where you need to be neat and make sure the separation between waves here and here is still the same as up here. In fact, you probably want to use a compass for this to try and make it extra neat, but I'm just going to do it freehand because I think I can back myself on how neat I am. Right, neat enough, and I'll just quickly show that. So the same, just if you're super messy. So the lambda is the same. We need to make sure that we state that the wavelength doesn't change when diffraction happens, not refraction. Right, so now we've got Tom and Alan standing on the beach watching waves. Notice the wave fronts are close together when they reach the shallow water as compared to the distance between the waves fronts and the deep water. I sort of drew a diagram so I can think of it in my head. I've got deep water over here. I'm going to call this 1. I'm going to have shallow water over here. Shallow. This side is going to be called 2. So anything on the deep side, any sort of velocities, wavelengths, yada yada yada, we have subscript 1. So let's just write down what we've got. V1's the velocity in the deep water is 12 meters per second. 12 meters per second, -1. Shift it up a little bit so you can see. What else have we got? V2, velocity in the shallow water, 4.5 meters per second. Lambda 1, the wavelength in the deep water is 12 meters per second. Meters per second. Lambda 2. We haven't been given that, but I can see distance between the wave crest and the shallow water. We don't know what that is, but we're going to have to calculate that. So let's put a question mark around there. And the frequency, let's start off with the frequency because it's probably going to be easier. So from the formula, velocity equals frequency times the wavelength, V equals F lambda. F equals velocity divided by the wavelength, which equals 12 divided by 1.75 equals 6.9 hertz. And just to double check, what's my least amount of significant figures? Right, 4.5. So I need two significant figures. 1.75 is 3, 12.0 is 3. But you always use the least amount of significant figures when determining to write your answer. So this has to be in two significant figures, which means the wavelength in the shallow water needs to also be 2 significant figures. Right. Okay, that's the frequency calculated. Good. Distance between wave crests and the shallow water. So we got V1 over V2 equals lambda 1 over lambda 2, and you can flip this whole thing around, or V2 over V1 equals lambda 2 over lambda 1, and that's the same as lambda 1 times V2 over V1, which is equal to 1.75 times 4.5 over 12.0, which equals, remember it's going to be two significant figures, 0.66 meters. There we go. So wavelength, can we see that? Wavelength in shallow equals 0.66 meters per second -1, and F is equal to 6.9 hertz. Noticing that frequency doesn't change when we change mediums. Right. Two speakers are producing the same sound placed together. Same sound placed together. Tom walks along AB. Alan walks along CD. Describe the sound that Tom hears. Compare that sound. Compare the sound that Tom hears with the sound that Alan hears. So if you've done this experiment, it's quite fun. You set up two speakers, use a tone generator to play sort of 200-300 hertz, and walk across. And what you'll hear is we're going to have an antinode in the center because the path difference from this speaker to here and this speaker to here are the same, and then out to at some sort of angle, unless you calculate. I'm just guesstimating the angles. It's an antinode. What have I done here? Yeah. Right, so you always have an antinode in the center because the path difference between both speakers is the same. Then you have a node, then antinode, then node, then antinode, and so on and so forth, up until you get to the angle here of 90 degrees. Anyway, so as you can see, Tom walks through 1, 2, 3, 4, 5 nodal or antinodal lines, and Alan only walks through 3. So what will Tom hear? Tom will hear loud and quiet sounds closer together than Alan. So that's what he actually hears, and then closer together than Alan because, well, it's obvious from the diagram. I'll move this up a little bit higher. Closer together than Alan as he crosses more, and this explains it, nodal and antinodal lines. So this is why he hears loud and quiet sounds closer together than Alan lines and Alan. And this is because the further you get from well, that's not straight, is it? The speakers. Right, here we go. So, bullet point. Tom will hear loud and quiet sounds closer together than Alan as he crosses more nodal and antinodal lines than Alan. This is because the further you get from the speakers, the further apart the nodal and antinodal lines become. You can also, if you bunch the speakers closer together like so, the nodal and antinode lines spread out, and if you pull them apart like so, they all bunch together. And there are a few simulations online where you can look up this is called 2-point interference, 2-point interference, PHET, P-H-E-T has a few, so does, there's a site, P-H-E-T, PHET, interactive, and there's another site which I forget, but they also have it up there as well. I'm trying to think, no, I can't remember it, but if you just look up 2-point interference, there we go. Right, last question. Tom shines a red laser through 2 slits and gets the following pattern on the screen. What write a comprehensive explanation for why there are alternate bright and dark bands on the screen. In your answer, include concepts about path difference and interference. Right. So as you can barely see, these wee sort of spots here are meant to be the bright spots, dark spots, bright spots. Unfortunately, I'm cheap and print in black and white, but if this was printed in colour, they would be red. So write a comprehensive explanation for why this is the case. Right, bright bands, so constructive interference. Just write that down. Where interference So I've said the bright bands where constructive interference occurs. This is where the light arrives in phase, and this is where the path difference is a whole wavelength. The path God, terrible at spelling. Is a whole wavelength. In other words, if you find out how many wavelengths it is from one hole in the slit to this bright spot, and the other hole in the slit to this bright spot, and the difference between those two distances is an integer number of waves, or a whole number, such as 3 waves difference, or 3 wavelengths difference, or 2 wavelengths difference, and so on and so forth. Right. So that's sort of semi-explained, but we'll explain it a little more with the dark bands. So the dark bands are destructive interference due to destructive interference, and this is when the light arrives out of phase, and path difference, I've spelled it correctly this time, is half lambda, or 3/2 lambda, or 5/2 lambda, etc. In other words, when the waves are out of phase, so when I say out of phase, I'll probably draw a wee diagram down here, so let's try and draw this neatly. This, I'll just separate these two, out of phase by 180 degrees, but you're not expected that to know that exactly in level 2. So if this was meant to be my axis as well, I've drawn this terribly, but trying to explain it. So they're out of phase. I should be using a ruler and doing it neatly, but I'm not. And then if I draw this again, maybe I might try and do it better this time. These ones here, in phase. So constructive, and destructive. And this is why this pattern occurs. So you get destructive for the out of phase, and we get constructive for the in phase, right? So that, just double check we've actually answered the question first. Tom shines a red laser through the two slits, gets full pattern on the screen. Common explanation for why this occurs. Concepts, path difference. Have we talked about path difference? Yes, we have. And interference, yes, we have got constructive and destructive interference, and we've got path difference as well. And did we need to have phase? Probably not, but I stuck it in there just in case.